Next, we're going to talk about the ratio test. A ratio test has three cases, 1, 2, and 3. In all three cases, you start out taking the limit as n approaches infinity of the absolute value of the sequence function of a sub n plus 1 divided by a sub n. So you have to put in the n plus 1 binomial for all the n's in that sequence function and divide it by the original a sub n sequence function. Now, if the limit is less than 1, then that original series for a sub n is absolutely convergent. So if the limit is greater than 1 or equal to infinity, then the infinite series for a sub n is divergent. And if your limit is equal to 1, then the ratio test is inconclusive. So no conclusion can be drawn about the convergence or divergence for this infinite series. So special note, this ratio test is very useful for series that converge rapidly. So your dead giveaway is you're going to see factorials or exponentials within your sequence function. That's a hint to use the ratio test. So looking at an example, we're going to determine whether the series are absolutely convergent, conditionally convergent, or divergent. So as you can see, we have an infinite series, and n equals 1 to infinity. We have an exponential, negative 3 to the n power, and you have an n factorial. So this is definitely a ratio test. So we take the limit as n goes to infinity. The two places you see the n, you're going to write negative 3 to the n plus 1 over n plus 1, that binomial factorial. And then in the denominator is your original a sub n. But again, we don't divide by fractions here, so we're going to multiply by its reciprocal. And now we're going to do some factoring and canceling. So the negative 3 to the n plus 1 power is going to be negative 3 to the n times negative 3 if you want to the first. So we're just separating those two. The n plus 1 factorial, start with n plus 1, start counting backwards by ones, you run into n factorial. And now you can cancel the n factorials, you can cancel the negative 3n top and bottom, and then you're left with the limit as n goes to infinity of negative 3 over n plus 1, where, okay, the absolute value of negative 3 will always be 3. The bottom will always be positive, so we don't need the absolute value bars down there anymore. So as n goes to infinity, the bottom's getting bigger and bigger and bigger. The top stays the same, so my limit is 0, which is less than 1. So by case 1 of the ratio test, my original series is going to converge absolutely. All right, example 5. N to the n power, all over n factorial, another good ratio test here. So we're going to take the limit. Now notice how I set this up. I realized, well, when you're given a fraction here, you're going to be multiplying by its reciprocal. So I just flipped that right away to save myself a step. Our n plus 1 base and our n plus 1 power, there's 3n, so all three of those n's become n plus 1. And so now we're going to start breaking down. This will be n plus 1 to the n power times an n plus 1. My n plus 1 factorial will become n plus 1 to n factorial. So we can cancel the n plus 1 with this n plus 1, this n factorial with that n factorial. Rewrite our limit as the absolute value of n plus 1 to the nth power over n to the nth power. But here, we can rewrite this, since they're both to the nth power. Again, we don't need absolute value bars because we are starting at 1, heading towards infinity, so everything is going to be positive here. But I'm going to write this fraction all to the nth power. So now I am going to divide every term by n so I can find the limit. My first inkling is that the top is going to get bigger faster than the bottom, so this might converge, but I'm not quite sure because we're raising things to nth power. So dividing everybody by n, or if you want, write this as two separate fractions, n over n plus 1 over n. Well, n over n is 1. And so now, as n goes to infinity, this goes to 0. And you have 1 plus 0, but I'm still not sure because when we first start out, this is kind of like that 1 over n. And when we took the limit, we found out that, oh, with your p-series, 1 over n would diverge, but 1 over n squared would converge. So I'm kind of wondering what's going to happen here. So one thing that you can do is you could actually graph this, because this looks very familiar if you're experienced with exponential functions. So I went to my graphing calculator, put in 1 plus 1 over x raised to the x power. And if I graph that, here's my curve. And I chose my x-min to be at 0, and I went up to 40. And as you can see, it does increase really fast, but then it starts to flatten out. So I'm wondering, are we converging to some particular value? We're not going to infinity. We might be flattening out. Well, like I said, if you're really good with your exponential functions, this is the definition for base e. So I went to y sub 2, put in e, graphed that horizontal line, and sure enough, that blue curve is approaching the value of e. So now e is approximately 2.71, which is greater than 1, and case number 2 of the ratio test says if the limit's greater than 1 or goes to infinity, it's going to diverge. So yes, this is divergent. My original series is diverging. All right, example 6. The infinite series, we have 10 to the nth power over n plus 1 times 4 to the 2n plus 1 power. So again, exponentials increasing really fast or converging really fast. Let's use our ratio test. Now here, when you put in the n plus 1, you need an n plus 1 on the power of 10. You need an n plus 1 going in for that n, so the 1 plus the 1, that's what makes the 2. Be careful with the exponent here. You take out the n, replace it with the binomial n plus 1, which means you're going to have to distribute the 2 first to get 2n plus 2 plus 1. So that's going to simplify to 4 to the 2n plus 3. So if you don't want to write this twice, this second statement is just cleaning this up. Just wanted to put emphasis right here on how we should get the appropriate power. Big mistake here is usually 2n plus 1 plus 1, and they have a plus 2 instead of a plus 3. So again, we need to be careful. So we start factoring. We can break this 10 to the n plus 1 down to 10 to the n times 10 to the first. The 4 to the 2n plus 3, we're going to take out 2 4s, so that'll drop the 3 down to a 1. Again, if you were to multiply like bases, add the exponents. The 1 plus 2 is the 3. And now we'll start canceling. So the 4 to the 2n plus 1 cancels. The 10 to the n's cancel. And now I have 10 times the n plus 1 over n plus 2 squared times 4 squared, which will be 16. And we can reduce 10 over 16 to 5/8. So again, you could put the 5/8 in front of the limit if you wished. We can leave it here. You could multiply it through. But in either case, when you do take the limit here, looking at this polynomial rational function here, n to the first over n to the first, when you have the same powers top and bottom, you're heading towards the ratio of the leading coefficients, which is 1 over 1. So that fraction here is approaching 1. So 5/8 times 1 is 5/8. and 5/8 is less than 1. So we're back to case 1, where our original series is going to converge absolutely. So you have absolute convergency. And that wraps up our ratio test examples.